Okay, so let's see what we get for a nonlinear first order differential equation. And so the differential equation that we are considering here is y prime equals 1 minus y square, and the initial condition is that y of 0 is equal to 0. And so given this differential equation, we again take step sizes, different step sizes, and so there are 3 step size solutions compared here. So delta t of 0.2, 0.1, and 0.05 are compared here. And so 0.05 will have, this is the finest 0.05, which is going to have 10 steps over this interval. And so overall is going to have 10 plus 10 plus 10 plus 10, so total 40 steps, and red is the exact solution. And so we can again see that as we refine, as we go from 0.2 to 0.1 and 0.05, the solution goes towards the exact solution as shown in this graph. And I should mention that these are all obtained with the first order Euler scheme. So the first order Euler scheme is very, very easy to implement and has trivial cost associated with it, and it is capturing this behavior. Of course, it has significant error which requires a finer and finer step size to remove, and so we can quantify now the difference between these curves. I should say that we've been calling this y, and the plot somehow we decided to call it u, but you can fix that difference. And so now we want to quantify this error. So here we are plotting the error norms that are seen with the first order Euler method here, 2 norm, and in blue we have the 1 norm of the error, and we have in red the infinity norm of the error, plotted on log scale, the error on log scale, and time step size on log scale on the horizontal axis. And for first order Euler, we would expect that these errors will decrease in proportion to the time step, and that is what we see here in this log scale. Of course, if we chose linear scales, it will also be a straight line, but only for when the order is 1 does this happen, that both log and linear plots produce the same slope. Of course, for a quadratic behavior or second order scheme on a log plot, the slope would become 2. So we are looking at the second order Euler method applied here to this nonlinear differential equation, and we can see that the different black curves are virtually indistinguishable from the red curve, and those were obtained with delta t of 0.2, 0.1, and 0.05. And on this visual representation, we don't see much of a difference. The solution is pretty accurate, and of course the nature of the solution, which analytically we can predict, is a tangent hyperbolic function and so on. That's something that one can anticipate by sort of qualitatively looking at the solution as well. That was the differential equation, and the initial condition was that y of 0 was 0. So initially when y is small, the rate of change of y with time is 1, and then as y builds up with that growth, it reduces the slope, and so it increases rapidly, and then the slope reduces, and as y goes towards 1, a slope goes to 0. So this solution asymptotically essentially cannot exceed 1. It's limited by 1. It sort of approaches 1 as time goes to infinity, and that's the nature we can anticipate, and that is what the numerical solution is showing. And so now if we quantify the error which is obtained with the second order scheme, we can plot that, and that is what we're going to look next. So here we plot the error norms. Again, a quick reminder that the error norm, 2 norm, is plotted in black. The blue curves are the 1 norm, and finally the infinity norm is plotted in red, and these norms now show a rapid decline as time step is reduced. We see a dramatic reduction in error, and if we follow the slope of this reduction, you would see that the slope is 2, so error is decreasing in proportion to the square of the time step. Time step is being reduced. Every time time step is reduced by a factor of 2, error reduces by a factor of 4, and that is something you can see here. And this is something that if you plot log plots, you will have a visual sense. This is a factor of 2 here. This is a factor of 2 increase because this is 0.01 and this is 0.02. And so if we compare the number here with the number there, that is a factor of 4 decrease. And how can I tell that? Is because this is 10 to the minus 3, this is factor of 2, this is 3, and this is 4. So this distance on this log plot is a factor of 4, and so if we compare the distance that we have here, this distance with that distance, you can see that in fact they are the same. This factor of 2 reduction in delta t brings about a factor of 4 reduction in the error, and this is something that we can investigate directly in terms of the numbers, but we can see that the slope here is 2. And so we have quadratic convergence, error decreases, and again we can observe that for a given error one can find what delta t it would take to achieve that error in an overall solution. And finally we can observe that, as we saw for the linear differential equation, for this nonlinear differential equation, the second order method is much more efficient. It gets to smaller errors much more efficiently. For fixed delta t, the error is small to begin with, and it reduces very dramatically. Of course, to balance that, we have to also observe that the number of arithmetic operations that are required per time step are twice what the first order method has. And so as you go to even more higher order methods, then that becomes a consideration. What is the extra cost and what is the benefit? And the two have to be compared to decide what is worthwhile for a practical problem. So we can conclude that this simple approach for integrating the differential equations can be applied to linear and nonlinear problems, and we can write more complex problems in terms of systems of first order differential equations, and thereby we can apply what we have learned here to even more complex and more interesting application problems.